Models for population growth. The law of natural growth. In the absence of other threatening factors to the population, not just human but any quantity, it is reasonable to assume that the growth rate is proportional to the size of the population, that is, dp over dt equals kp, where k is a constant. So p of t is the value of a quantity y at time t. This is called the natural growth. If k is positive and p is positive, then dp over dt is positive. Notice that dp over dt is 0 only when p is 0. The second derivative of p is the derivative of dp over dt, which is the derivative of kp, but k is a constant, so we can factor it out to get k times, but dp over dt is kp. And so the second derivative is k squared p, which is always positive. dp over dt equals kp is called a autonomous differential equation because it only depends on p. To learn more about this differential equation, we construct a phase line. We see that the first derivative is positive, so the function is increasing. The second derivative is positive, so the function is concave up. A phase line is a plot on the y-axis that shows the equation equilibrium values along the intervals where the first and the second derivative are either positive or negative. By looking at the sign of the first and the second derivative on the phase line, we know whether the solutions are increasing and decreasing, concave up or concave down. The autonomous differential equation dy dt equals ky can be solved using separable. We integrate both sides. After we separate it, we get ln of y equals kt plus c, e both sides of the equation to get y by itself, plus or minus because of the absolute value, e to the kt times e to the c power. But if we let a equals plus or minus e to the c, the solution is a e to the kt. And so if dp over dt equals kp, then the solution is p equals p naught e to the kt, where p is the function of t. Also, when t is 0, p of 0 is p naught. This is called the initial condition.